So this is a two-dimensional object. So the mass density is going to be the mass divided by the area of the object. What's the area of a disk? It's pi a squared. Yeah, a is the radius. All right. And then if I divide the disk into rings, small rings, thin rings of mass delta M and area delta A. Oh yeah, I should have started by that, sorry. Area of a ring delta A. What's the area of this yellow part here of the disk? It's going to be the radius times the width. Oh, sorry, it's going to be the perimeter times the width. The perimeter, if I'm distance r from the center, the perimeter is going to be 2 pi r, and the width, I'm going to call that delta r. It's small. It's going to be 2 pi r delta r. So since the mass density is also that, I can find the mass of a ring. Delta M is going to be rho delta A. Delta I have it just here. And rho, I also have it, M pi A squared, delta A, 2 pi R delta R. So I end up with the pi's cancel out, 2m a squared r delta r. Now that I have the mass of the ring, I can compute the moment of inertia of the ring, of each small ring here. I'm going to call it delta IZ, and it's going to be delta M R squared. Right? I remember that a ring of radius A and mass M has moment of inertia M A squared. Here the mass is delta M, the radius is R. Okay, so I just write that now with my formula above, 2M over A squared R cubed now, delta R times R squared is R cubed. And then, you've guessed it, yeah, I'm going to add up to find the total moment of inertia. It's going to be the sum of all the rings, 2m a squared R cubed delta R. And now I'm going to say that this sum here is an approximation of the area underneath the curve y equals 2m over a squared r cubed. Because if I draw little rectangles under that curve, and each rectangle has a width delta r, and add them all up, I'm going to get something close to the area. And then if I take the width of each rectangle to go to 0, I'm going to get the exact area, and that's the integral. So as delta r goes to 0, that's going to tend to the integral. I'm integrating from 0 to a of 2m r cubed delta, no, dr now. And so I get the idea now of the resolution. I'm just going to have to compute an integral. What's the integral of r cubed? It's r to the power 4. Almost, right? If I had r to the power 4 and I differentiated, I would get 4r cubed. I don't want that 4, so I have to divide by 4. I get my integral. I evaluate it at a. and then at 0, and I end up with 2m over a squared, a to the power 4 over 4. Finally, I've just shown that the moment of inertia of a disk is 1/2 m a squared. And I think that's in the logbook. I need that to compute the angular momentum and then to write the balance of angular momentum equation, or to compute the kinetic energy and then to write the conservation of energy, or so on and so forth, just to solve the problem of a rotating disk, for instance. All right? Angular momentum about, and that's the part that you mustn't forget, that's all relative to an axis. So if the disk was rotating about its axis of symmetry, then I would find Jz, and that's Iz omega, so it would be 1/2 m squared omega. And then similarly, the kinetic energy could be 1/2 Iz omega squared. Omega squared. Right? That's why we're computing those moments of inertia, because of those formulas here. Moment of inertia is to rotation what mass is to motion of a particle. And then velocity is to the motion of a particle. Oh, sorry, angular velocity is the counterpart to velocity for a particle. And v 1/2 of mv squared, or I omega 1/2 of I omega squared. But then, of course, here I'm only doing rotation about the axis. What if I was rotating about another axis? What if I was rotating along a diameter, for instance? Presumably, it would be different calculation. And then you realize that moment of inertia is, in fact, a matrix. So what is the matrix? Okay, any questions? You get the gist. It's very much like when we were computing the center of inertia. You divide the object into small object for which you know the answer. So for the small object, then you compute the area, the volume, or the length. And you deduce the mass from the mass density, which is the same all across. And then you can add up, take the limit, end up with an integral. Numbers, yeah. In the end, we'll have to put numbers. But you need the formula before you can do numbers. And the formula is in the book, so you don't need to memorize it. But you need the formula, right? In the book, if they said moment of inertia of a disk, radius 3 and mass 4, and then they just give you Iz equals 8, r squared, 8, that's it, you wouldn't be very illuminated by it. You need a formula that works everywhere, and then you do an example. We will do examples, don't worry. So we've done the disk, we've done the rings, the cylinder. You could do the same for a full cylinder, and you will find that it's the same formula. Makes sense, right? You're just going to divide the cylinder into small disks. Each disk will have this moment of inertia up there, with m the mass of each disk. Then you stack them up, you're going to have the total mass of the cylinder. That's easy. What about a rod? What if I have a rod of length 2a rotating about this axis, perpendicular axis? What you're going to do is divide the rod into small elements. So now we have a one-dimensional material, just x between minus a and plus a, small elements of length delta a, small length element, oh, delta x, sorry. So length of element delta x, mass density is the same everywhere, so the mass density for an element or for the whole rod is the same. For the whole rod, it's going to be m over total length, which is 2a. For small element, it's going to be delta m over delta x. So from this, I can deduce the mass of an element delta m over delta x. Oh, that one's going to be easy. So then I can find the mass, sorry, the moment of inertia of an element. I know that it's going to be ma squared, mr squared, or here it's going to be delta m x squared. This is the mass rotating about the axis. That's the definition of the moment of inertia. Then I just replace m over 2a x squared delta x, and then I add them all up to get the total moment of inertia, sum over the elements delta iz. So same technique, m over 2a. That's the sum of little rectangles under the curve of this function here, m over 2a x squared. If I take the width of the, so sorry, that's the sum of the area of little rectangles under the curve. If I take the width of the rectangle to go to 0, then the area of all the sum of all these rectangles is going to tend towards the exact area under the curve, which is the integral. So here I'm integrating from minus a to a, or 2a x squared dx, and then that's easy to compute. I simply have to integrate x squared. What's the integral of x squared? It's x cubed, right? Am I right? Right on the right. All right? No? No. I forgot the 3, right? If I go back now, if I differentiate x cubed, I will get 3x squared. I don't want 3x squared. I just want x squared. So I prevent that by putting 1/3. Then when I differentiate x cubed over 3, I just won't get x squared. Yes, so that's good. Then I evaluate it at a cubed over 3, and then minus a. Have to be careful here. Because minus a cubed is minus a. Minus a cubed is minus a cubed. Sorry, the intonation, right? A cubed over 3 minus, and the minus, there's going to be a plus, times 2a cubed over 3. Oh, I don't have room. I'll write in different color then. IZ equals, the 2's cancel out, I'm going to leave left with 1/3 ma squared. Yeah, the 2's cancel out, a cubed divided by a squared. Okay. And so again, now that I have this, I can go on and solve a problem of rotating rod. Nice. The angular momentum, I know it's going to be IZ omega. The kinetic energy about OZ. Just reminding you that I is dependent to M. Okay. So that's for a rod rotating on an axis going to its center. Rod rotating like this, nothing's going to happen if it's just a one-dimensional object. What about a rod rotating like this? About this axis? Surely it's different. Can we find? We can do it. We can do the parallel axis theorem. Brilliant. We can do it in all generality. So it's a nice proof. I'm going to do that. First we take a break. Okay. So now the parallel axis theorem. Like I said, do we have to do all those calculations each time? Take a body, compute the moment of inertia respect to an axis, and then if I want to do rotation respect to another axis, do I have to do the integral again and so on and so forth? No, I don't have to. As long as I'm doing rotation about a parallel axis to the one I already know, I can just deduce the moment of inertia. Amazing. And very easy to prove. I'll show it to you now. So say I have, a body here, so any shape. Is the center of mass somewhere. And here's the axis Z. And I know the center of, the moment of inertia with respect to this axis, rotation about this axis, just like in the examples before. If I wanted to find now moment of inertia with respect to that axis, a parallel axis, like I say, moving from rotation about this axis here to rotation about this axis there, I can just do it, all right? I'm going to go A, the distance between the two axes, and then, that's the parallel axis theorem, IZ prime, IZ plus MA squared. Very simple. So I don't need to redo the calculation. So I can just look up in the book or in tables. You will find those expressions there, and then I could just deduce the other ones. Let's read what's written. Let IZ be the moment of inertia of a rigid body of mass m above an axis going through the center of mass. Let IZ prime be the moment of the parallel axis. Okay, so there's origins here. There's another origin here. O prime, Z prime, perpendicular distance A. Then IZ, well, I just written. And like I just told you, those moments of inertia is going through the center of mass. You'll find them in books, in tables. It's rarely asked to memorize them or to calculate them. And then, using parallel axis, you can find it with respect to any axis. Well, parallel ones at least. So you can see that ma squared, that's positive quantity, so Iz prime is always greater than Iz. Iz is the minimal moment of inertia. So we're just going to prove that. It's not that difficult to prove. If I have my body here, my axis Z, and the particle mass mi, generic particle inside the body, and then further away I have Z prime, another origin O prime, and then I look from above at the horizontal cross section. It's going to look like this, right? It's going to be this intersection here. Mi, I should have put it somewhere else maybe. Mi, putting it here. It's going to look like this. I have O, and I have Ri. Ri, that's the position vector of the mass, of the particle mass Mi with respect to the origin. And then if I go towards the other axis, I have this vector A here. And then between the two, I have Ri prime, which is the position of Mi relative to that intersection here of the horizontal plane with the Z prime axis. So now I can compute the moment of inertia about OZ prime and see if I can connect it to the moment of inertia about OZ. So let's do that. Moment of inertia of Mi is, so by definition, is the mass times the square of the distance, right? The distance here is going to be Ri prime squared. I can write it like this: Mi Ri prime dot Ri prime, and Ri prime, this vector here, to go from here to here, I can go this way, minus A plus Ri. Right? There to there it's that way, minus A plus Ri. Yeah. So now if I do moment of inertia of the whole body, I'm going to have to sum. I'm going to write Iz prime is the sum of all these over I of Mi Z dot Ri minus A. Okay, I have a dot product, I can expand. What's the first term? Ri dot Ri, so that's nice. I recognize Iz here. Then I'm going to do minus A dot minus A, so that's going to be plus. And then finally I have the cross terms, minus A dot Ri minus Ri dot S. That's twice. A dot Ri. Okay, I can see I'm nearly there. This part here, that's Iz. This part here, I see I'm only summing on the Mi. Sum of the Mi, that's the total mass. And then A dot A, that's A squared. So I have my theorem, Iz prime equals Iz plus A squared, provided this is 0. Is it though? Doesn't look like it's 0. Huh. Let's have a closer look at this quantity. Is it really 0? Ma. Okay, I can see that the A is a factor in here. Mi. MIRI. Oh yes, I can write M and 1 over M. That doesn't change anything. But this here what is it? I recognize it as the horizontal component of the position of the center of mass. Yes. Remember? Mi little ri sum all this, that's the position of center of mass. Capital R's are only in the horizontal plane, so that's the horizontal component mass position vector. And then that's 0 because OZ goes through the center of mass. And so, indeed, this quantity here is 0. And I've proven my theorem. Piece of cake. Now you can have your cake and eat it. Never understood that expression. Why do people say you can't have your cake and eat it? I can have my cake and I eat it. What's the problem? I don't get it. You get it? I don't get it. I can't eat my cake and have it. I get that. If I eat my cake, then I don't eat it. But I can have my cake and eat it. No? I don't understand. Then there's the doesn't cut the custard or doesn't cut the mustard. What is it? The mustard or custard? That I understand, right? It's easy to cut mustard, so if you cut mustard and it's not very strong. What about passing mustard? Expressions are funny. Okay, so now we can answer this question. What's the moment of inertia with this mass M? Is my disk rotating about this axis? Interesting point. An axis perpendicular to the disk, but just touching it on the edge. So I know that Iz prime by the parallel axis theorem, if I call Z the axis going through the center of the disk, Iz prime is going to be Iz plus MA squared. And just earlier I showed that Iz was a half of MA squared. And so I end up with 3/2 MA squared. Easy. And now we can do finally this one. Rod rotating about its edge. Oh, actually, even more than that. So you have a rod of length 2b. And it's rotating about any vertical axis, Z prime, provided the distance between the center of the rod and Z prime is called A. That didn't work. Let's do this. Whole thing works. Okay, I'll do it again then. What's going on? Ah. Okay. Well, I know the moment of inertia with respect to this axis here, Iz is let's go back to what we did earlier. Here was 1/3 of MA squared. If A is half the length of the rod, so here half the length of the rod is B, so it's going to be 1/3 MB squared. And then by the parallel axis theorem, so I'm going to end up with 1/3 of MB squared, MA squared, and so on and so forth. Not that difficult. Nice. So we can do a lot now. Now we could send a rod in the air, rotating about its axis. Center mass going to describe parabolic trajectory, and then we can find the velocity, angular velocity, by solving the balance of angular momentum. Any question? Any question about the test tomorrow? No? 8 questions, yes. So be there on time. Best of luck. It's a good training for the exam, which might not take place. Who knows?